In the next couple of lessons, we're going to look at nuclear fusion and then at nuclear fission, and in between we're also going to look at how stars are formed. In order to understand the process behind the life and death of stars, we need to understand nuclear fusion. So the idea for the next few minutes is to understand what is meant by nuclear fusion. It's important to be able to explain the conditions for nuclear fusion to occur. We're going to talk about some fusion equations, and then right at the end we'll look at why science is interested in nuclear fusion. So we'll start off first of all by just defining what we mean by nuclear fusion. The word fusion means joining two things together. There's many uses of the word you might have heard. Fusion restaurants bring two different types of food together. So nuclear fusion is when you bring two nuclei together. The simplest fusion is joining together of two hydrogen nuclei. So if you start off with two hydrogen nuclei, you fuse them together, you're going to end up with something different, and we end up making helium. But the key thing is energy is released in the process. It's absolutely crucial, fusion is, because basically every little piece of energy, all energy in the universe starts from nuclear fusion. And all the atoms bigger than hydrogen, so that's every single atom. Hydrogen has just got the one proton. Every other atom was formed doing nuclear fusion, so fusing hydrogen together to make larger and larger atoms. So every atom in your body, except for the hydrogen, you could argue must have once been in the centre of a star and formed by a star. We'll talk about that in the next lesson on star formation. Okay, so this little model gives us an idea of fusion occurring, and let's see if we can get fusion to occur at a temperature of about 1,000,000 degrees C. Here we're going to take hydrogen 2, which consists of a proton and a neutron, and we're going to see if we can fuse it with hydrogen 3, which consists of a proton and 2 neutrons. If you think back to your previous work in science, temperature relates really to how fast the atoms within a gas move. So these two nuclei are going to move quite fast at 1,000,000 degrees C. Let's see if we can get them to fuse, and from the model they don't quite really get close enough. The idea being here, you've got to remember, is that both of these nuclei are positive. So because they are both positive, they repel each other. So at 1,000,000 degrees C, they're just not moving fast enough to get close enough to fuse together. So we'd have to up the temperature. So if we try 10 million degrees, still got hydrogen 2 and still got hydrogen 3, trying to fuse them. So have a look, they're going a lot faster, but they don't fuse still. They are not moving fast enough to fuse together. So we'd have to go up to temperature of about 15 million degrees C. Let's see if these will fuse together, and brilliant, there we go, a little bit of a sound effect as well. They have fused together, and we've ended up with something different to what we started with. If we just go back, notice here we've got hydrogen 2, known as deuterium, and this has got one proton and one neutron. This is hydrogen 3, also known as tritium. This has got one proton and 2 neutrons. When we fuse them together, we end up with helium, which has got 2 protons and 2 neutrons, and we've also got a spare neutron left over. If we count up the number of protons, we've got 2, we started off with 2, and if we count up the number of neutrons, we've got 3, and we started off with 3. So this is the fusion equation we've been talking about earlier. So we've got deuterium fused with tritium, or hydrogen 2 fused with hydrogen 3, and we ended up with helium and a spare neutron. And most importantly, energy was produced. So in doing this fusion, there was energy released in the process, and this is released when the protons and neutrons are rearranged to form a different nucleus. We have energy being released. So in summary, what are the conditions for nuclear fusion? We need a very high temperature. We need a lot of energy for this reaction to occur, for this fusion reaction to occur, as we've seen. So stars are very, very hot, and they have the perfect conditions for fusion to occur, because the very high temperatures and pressures at the centre of stars gets these atoms, gets these nuclei, moving at the speeds that we need to get them to fuse together. The reason being, remember, is that they repel each other. They're both positive, so we need to get them moving quickly in order for them to fuse. Why are we interested in fusion? Well, the biggest reason that we are is that if we could do fusion on Earth, if humans could do fusion, then the energy that's released in the process we could use to generate electricity. That energy, in simple terms, the energy would be used to boil water to create steam, and that steam can turn turbines and generators just in the same way that it does now with a coal-fired or a nuclear fission powered power station, which we'll talk about in the next lesson. So it really would be useful, it would be fantastic to be able to do nuclear fusion on Earth. But we've done lots of testing, and they do just about work at the moment, but the problem is that, as you've seen, we need really high temperatures, much hotter than the sun, because we've got to get to the temperatures at the centre of the stars, the centre of suns. So we need really hot temperatures and high pressures. So it's very, very expensive. And the biggest problem we've got at the moment is that it's pointless doing, because the electricity and the energy we use to cause fusion is more than the energy or the electricity we can get out. So at the moment it's not very good, but research is still going on. This is the pros and the cons, the good points and the bad points. Fusion will create a lot less nuclear waste than nuclear fission, which we'll talk about later. The fuel is fairly readily available. We've just seen it's hydrogen, which we can get from seawater. The only product is helium, which is not reactive, it's not radioactive, it's a clean product, so it'd be fantastic, and in the process lots of energy is released. The cons or the bad points about this, that the temperature and the pressure is difficult to achieve in a reactor. It has been done, but it's very, very expensive, and we need to use powerful magnets and lots of electricity to contain the high temperature fuels. So at the moment it's not a viable option to generate electricity, but hopefully in the future it will become viable.